All right, yeah, so in the future, if you ever want to join. Okay, I didn't hear. Anyway, yeah, if you ever want to join real time remotely, you can go to the link that I shared, and you can always join. Yeah, so I post the meeting ID on that before the class, so you can always access through there. And two announcements. One is on Thursday, homework 2 and lab 1 are due. We're doing okay? Okay. So mostly, okay, good. So I think I will keep that that line in. I canceled my office hour this morning for this afternoon, but tomorrow I have one more hour if you want to come by to ask questions. And the other announcement is about the data cam courses. So make sure that the one I said it to do, Introduction to R, is due today. And the other one, Intermediate R, is due 1 week from today. So make sure that you catch up with that, especially for those who don't use R that often. I think that can help you to get up to the speed of what we do in this course. Okay. So all right. So for today and tomorrow and Thursday and maybe a little bit on next Tuesday, the topic is Bayesian inference for a mean. And as you can see, now we're moving from a categorical or binary, I should say, categorical variable now to a continuous variable, which is the mean. And you'll see that we're going to definitely talk about how to think about the data model and then how to think about setting up higher distribution for a particular parameter. Here is the mean of a continuous variable. And then how to, so there's certain conjugacy that can work here as well, so which we're going to go into detail. Then, of course, once we know the prior, how to update to posterior. So we're still going to work with conjugacy. There's some derivation involved, a little bit more complicated than before, but the general idea is the same, that you're trying to collect terms and then trying to recognize in the posterior. Okay, and this is still falls into the category of a one parameter model. So remember, for the beta binomial, we have only one parameter, which is the proportion, the unknown parameter, and then in the binomial model, and so that's a one parameter model. Here in a minute, you're going to see that the data model that we're going to work with is normal. So normal density, we now have 2 parameters, okay, mean and the standard deviation or variance or precision, whichever way you define. And for now, in this unit, we're going to focus on still just making inference for one parameter out of the 2. That means we're going to fix the other one, suppose that we know it, and still treat it as one parameter model. And then moving forward, you will see that in next unit, which is keep sampler and MCMC, we're going to actually we're looking at the Bayesian inference for using the normal density model. And there we're going to look at, well, what if 2 parameters are both unknown? Okay, so how are we going to do that? So so for now, we're still going to keep it as a 1 parameter model so we can get more familiar with how, say, like the derivation, how the update, and how the coding works. And then we'll move to next unit, you're going to see, well, if conjugacy doesn't work, what else we can do? And that's how the computation techniques can help us greatly. Okay. All right. So that's roughly the agenda. So for today, I'm going to bring in a new example. And using that example, we're going to look at, say, the mean and standard deviation. If we fix one and let the other one to be unknown and random, then we are able to actually give conjugate prior and posterior, and then arrive at conjugate posteriors for this 2 separately. So we're going to walk through that today. Hopefully most of this can be done. And then on Thursday, I will do a little bit more lecturing. And then for the Bayesian inference, remember, we do hypothesis testing, credible intervals, as well as prediction and posterior predictive checking. So all of those can be done in this context as well. So I will create a lab instruction that we can actually work on the computer, on your own computer on Thursday, so you can get more interactive. Because otherwise I can lecture, but it's a lot of, I wouldn't say repeating, but it's going to be very similar to what we have done before, and I want it to be a more active learning for you all. Okay? So that's the plan. All right, so the example that I'm bringing in today is the expenditures in the consumer expenditure survey. So this is a survey I've been working with in Washington, D.C. for a little while, so I got a little bit more familiar with what they do over here. So I wanted to introduce you a little bit about a lot of the survey out there in the US, and in particular this consumer expenditure surveys, how that is helping us learning about the buying or purchasing habits of US consumers, I should say. So the consumer expenditure surveys data, we call it CE. It's a survey conducted by the US Census Bureau for the Bureau of Labor Statistics. And it contains data, as you can see, I just listed a few, expenditures, income, and tax statistics about consumer units. So we use CU as abbreviation for consumer units. You can understand consumer units as just a household with family. Most likely, it's people living in the same household typically, and across the country. So they collect data on this, and then they release data to the public based on what they collect. And if you go to their website, you will notice that they produce some release data in two ways. One is tabular data, so it's aggregated. For example, they do tabulation of like certain income group and gender group or race group, et cetera, so you can get some kind of summary statistics out of that. They definitely not only produce a point estimate, but also that uncertainty, like standard deviation, that kind of estimation, standard error, I should say, for those summary statistics. So those will be useful if you want to know aggregated level data. And at the same time, they also provide what they call micro level data at PMUD. So it's public use micro data. I think that's what it stands for. So this is reported at the CU level. So you can think of, like, for a particular consumer unit, you can have information about their expenditure, their income, tax statistics, et cetera, et cetera. So those are not aggregated. It's at the respondent level. So with those access to the second type, if you want to do detailed statistical analysis, especially say if you want to run like a regression, those type of data will be super useful. Okay, so they report both, and we're gonna look at the second type in this example by understanding, say, how the expenditure is being. How can we like understand the expenditure of consumer units in the U.S. So the particular micro data variable that I focus on here is a continuous variable. It's called TOTEXPPQ. It's the CU total expenditure from last quarter. Okay, so it's a public available data, and the sample that I get for us is from the first quarter from 2017, and the number of CUs in that sample is a little bit over 6,000. Okay, so this is the scope that we're working with. And we're working with a continuous variable. So when you, like, say, trying to understand a particular variable, a good thing to do in the first place is to plot it. So I plot this for you, and this is the code that you can use. I posted on Moodle as well. And this is just the raw data. I'm plotting the total expenditure from last quarter. And as you can see, it's pretty right skew, extremely right skew, I should say, which is not too surprising if you think about its expenditure from households or consumer units. And I also provide some little summary on the left bottom. And this, again, you can get it from the summary command from R. So as you can see, in order to model this particular variable, especially earlier I mentioned that we're going to use a normal model. I think everybody knows about the normal distribution. This might not be a good, looking at this, the density of this total expenditure from last quarter, normal might not be the best choice because it's pretty right skewed, right? So a typical practice that people do is you can take the log and then you can transform to the log scale. So what I do is you can transform it into the log scale. So that's the code. And then now we're working with a more, I should say, symmetric bell-shaped distribution. Okay, so this is the one that we're going to work with. So we're focusing on the log scale of this total expenditure. And this is the variable that we are trying to understand. All right, so just a little bit overview or review of the normal distribution. It is symmetric, bell-shaped, and it has two parameters, the mean, we use mu, and standard deviation, sigma. And the density, so if you have a random variable y follows a normal mu sigma, then the PDF is what I present in equation 1. So the range, as you can see, of the random variable is from negative infinity to positive infinity. it centers at the mean. So as you can see in the exponent, you will have y minus mu. So that's where it's centered, and sigma, the standard deviation, is controlling the spread. Right? So the plot down here, I just got it from a line. As you can see, so it's centered at the mean. So it's color coded for different normal distribution. So 3 of them are centered as 0. So mu, yeah, the first 3, the blue, the yellow, and the red, they are all at mean 0, but they have different variance. So sigma squared variance. And as you can see, the larger the variance, the larger the spread. So the highest, I mean, the tallest one is the blue one, which has a variance of 0.2. And then as you gradually increase the variance from blue to red, you see that it's still centered at mu, but then it's going shorter and then fatter on the tails. And then if you keep going to the yellow curve, which has variance of 5, it's even bigger spread. Okay, so that's the general shape. And then, of course, the mean is also, you can also, it's a random variable, and you will, in parameter here, you're able to change that as well. Say if you have a mean to be -2, you will see that the green curve now is centered as -2, okay, with the different variance. So this is the general shape, and then the PDF, keep in mind, this is the one that we're going to work with pretty closely. We're trying to derive, as you can see later, we're going to derive the posterior. And so we're going to work with this closely. I will show other places of the PDF as well. So one thing, we talked a little bit, I think, in the introduction lecture about exchangeability, as well as like independent and identically distributed variables. So here, we're assuming that we have a sequence of n responses, y1 through yn. And what we're doing, so pretty much we're saying that for each CU, the expenditure, the log expenditure from last quarter is identically and independently and identically distributed following a normal distribution. So we write, you have this tilde, and then on top of that is IID, and then each YI is IID, normal mu sigma. So once we do that, so independent and identical. So independent meaning that they're independent from each other. So the joint density can be the product of the marginal. Okay, so that's how in equation 3 you would have this product. So the product actually governs the entire part. Okay, and identical meaning that they each follows the same normal distribution. So that's why you have the same PDF for each of the observations. So to start with, if they're IID normal with mean mu and sigma, standard deviation is sigma, then you will have the joint density to be this, and then each of the yi is from -infinity to +infinity. Okay, so the product, and then so the product governs the entire thing. Okay, so it's n copies of each PDF, marginal PDF. But then again, because yi is different, you won't be able to simplify further. You can simplify them this part, but later you can bring this to the power of n. That's fine. We're going to see that. But for the exponent over here, this is important to know that they're different. So this is a starting point. As you can see, this is the joint density. So later, we will remember in the beta binomial case, we are using the binomial density for the data model, right? So we use that, and then we actually write the likelihood function. We express the data density in terms of the unknown parameter. So this is what we're going to work with later when we start to rewrite it in terms of the unknown parameter. So this is almost likelihood function, except right now it's still written in terms of the normal density for both parameters. So you see that mu and sigma, right? And both of this usually are unknown. And now moving forward, I'm going to fix one of this and then do only consider the other one to be unknown and random. So when we're trying to write the likelihood function, we're going to assume the other one is known. So that later on, as you can imagine, we're trying to derive the posterior. It's going to consider as constant. then they can go into those proportional signs. Okay, so keep in mind that normal model does have two unknown parameters, but to keep the process simple and to get us started, we're going to fix one of this and then treat it as a one parameter model. So the prior and then the likelihood will be in terms of the unknown parameter, and then when we do the derivation for the posterior, it's also we're only going to care about the unknown parameter, only one. Okay, the other one is fixed. All right, so keep this in mind, and we can start working. I think I will just do this as two the same. All right, so there are two parts. Let me actually just pause this.